Thanks, Paul. I had a whole slide on that. Thanks, Paul. So just a brief introduction about Databricks. So I'm a solutions architect at Databricks, so I work with our customers on solving Spark-related issues. So just a brief background before the talk. Databricks is founded by the creators of Spark, and we provide a cloud enterprise data platform which comes with managed Spark clusters, and it has notebooks for doing interactive data science and then running production jobs, all with like enterprise-grade security. So the reason is today's talk is about Spark streaming, the best practices. So this comes from my experience working with our customers, making them run Spark streaming in production. So the agenda is like give a brief introduction to Spark streaming, how it works, and then go a little bit in depth about a life cycle of a Spark streaming app. And then, so that should set the context for the remaining two sections, which is the aggregations and the state management that can be done on Spark streaming and the best practices for doing them. And finally, operationalization tips and key benefits for of using Spark streaming. So what is Spark streaming? So Spark streaming provides a high-level API on top of Spark's RDDs to do joins and window-based aggregations. So it's mostly like it has similar interface like RDDs. The functional it follows the functional programming paradigm, and it guarantees exactly one semantics even for stateful operations. And you can integrate that with other libraries on top of Spark, MLlib or data frames or SQL. So in terms of people using it, there are more than 500 companies that are using it in production, some of the major ones. I've used that when I was at Netflix. So getting to the core part of how it works. In a nutshell, there are data streams coming in. So there is a receiver that Spark streaming kind of uses it to receive data continuously. And then it chops them into batches, sends it to the Spark core engine, and then pushes out the results to the sink. So that's in a nutshell at a very high level. I'll just walk through a word count example so that it sets the context for then subsequent sections. So any entry point for a streaming job is the streaming context, and you can create a streaming context by providing a batch interval as the parameter. So batch interval is the unit of time that Spark streaming uses to chop the data into batches, basically. So once you have a context, now you can provide a receiver, or you can specify the source information to say where the stream is coming from. So in this case, it's a simple socket text stream. And what you get back is the D stream. So D stream is the API that Spark streaming exposes to kind of do any transformations. So once you have a D stream, which represents a data stream, you can do further transformations on them to create newer D streams. So in this case, we got a lines D stream. So we are doing a flat map operation, which kind of splits all the input input text into words, and you have a words D stream. And then further, we can kind of do further transformations and do a final word count, get a final word count stream. And then here we are just printing the D stream contents onto the screen. So until now, like nothing happens. Once we do a streaming context at start, so that's when like the streaming job kicks in, like Spark goes ahead and sets up everything on the cluster, and the streaming job starts to run. So let's get on to how that works in order to kind of have an understanding about some of the best practices that we can follow while doing a streaming job. So this is the execution model in any Spark application. User code runs on the driver. As soon as there is like a distributed collection like RDD and there is transformation on it, Spark kind of pushes those operations to the executors and does them parallelly. And as far as a resource manager, people normally use Yarn or Mesos or Spark standalone. So this is the execution model for any Spark application. This is slightly different for a streaming application. So for a streaming application, the driver code starts execution on the driver, and as soon as there is a line for kind of a receiver, so Spark kind of chooses one of the executors and starts running a long running thread on one of the cores in that executor. So here you can see there is a receiver thread that gets started here, and that starts pulling in the data stream from its source, from wherever it is. And it starts storing them as data blocks in the executor. And if required, based on you can provide a parameter to spill it to disk if you think it won't fit into memory. And you can also specify a replication factor so that it kind of moves the data blocks to other nodes in case of a receiver failure. So that's the first part of a Spark streaming application, where it first sets the receivers. The second part is the actual execution of all the operations and the actions. So as soon as, so the operations and actions are basically the word count, the actual word count, doing a flat map, doing a reduce by key, and kind of doing all the logic to do the word count. So based on the batch interval provided, so here like if we provide a batch interval of 1 second, Spark streaming kind of picks that for every batch interval, it submits the jobs to the executors where the data is located, like just to have data locality. It executes the tasks and then pushes out the data to the sink. Just to go one level deeper, so this is a streaming application which kind of programmers write. This is an example here which has 2 socket streams, and then there is a union of the 2 socket streams, followed by 3 actions. The first one is basically saving it as Hadoop files. The second one is doing a map followed by a for each. So basically it kind of for each is any action. You can like do a print or push it to some other sink. Similarly, there is a filter followed by a for each. So what happens here is this program first gets compiled to a dstream graph. So here there are 2 receivers, followed by the union, followed by a common operation, and followed by the 3 gray ones which indicate the final output operations. So once this is there, the next step is like for every batch interval, Spark streaming will take this DAG and starts putting it into a queue. So the queue kind of, you can think of it as like a simple queue where all the DAGs are queued up for further execution. So this is the role of a Spark streaming, the core of Spark streaming. The next phase is where Spark picks up from this queue the first DAG, the first DAG that it needs to execute. It breaks them into stages, like wherever there are shuffle boundaries, like it breaks them into stages, and then it breaks the stages into further granular tasks, and then pushes it to the executors. So the executors is where the actual the data is being received and the data resides. So all this happens on the driver for every like a batch interval. If the batch interval is 1 second, then for every 1 second, like this DAG gets compiled, it is pushed to the queue, and then Spark picks from the queue, compiles the stages, and then breaks them into tasks and pushes it to the executor. So this is like in an end-to-end view of a Spark streaming app. So in terms of like aggregations, so we saw a word count. So word count, the first program, what it did was a word count for every 1 second. That's not a real world application in any sense. So the most common thing is doing word count over a time window, like for the last 10 minutes or for the last 5 minutes or even for the last 1 hour. So here each square basically represents a batch, and the dark green basically represents the entire window size that you want to do the word count for, and the lighter green represents the sliding interval. So it's basically like a tumbling window, so you can do a word count for every n seconds instead of doing for every second. So the best way to do that would be like you have a D stream, and then you can say, instead of just reduce by key, you can also specify a window parameter, and then specify the function, the aggregation function. In this case, it's a simple sum, followed by the window size, and then the sliding interval. So this is great, like it's a simple scenario, but most of the times I've seen like customers or some of our customers run into performance issues. So the common scenario is I want to do a word count for the last 30 minutes. I've set a batch interval of 1 second. So what's the problem? The problem is you have like Spark needs to go back to the last say 30 into 60, around 1800 batches to do the word count. So and Spark needs to finish all this doing word count across this 1800 batches in less than a second for the next batch to kick in. So this is a big problem. So one optimization is choose your batch interval wisely. Like, does it really have to be 1 second? Because if there are other operations that require it 1 second, you can keep it at 1 second, or you can bump up the batch interval to like 1 minute or so to kind of make sure that Spark is not processing too many batches, because each batch is basically an RDD, and that has partition, at least one partition in it. So it transforms to 1800 partitions. The second optimization is basically doing incremental aggregations. So here what you can do is, as new batches come in, you can just add them to the aggregation, and the old batches that are going out of the window, you can remove from the aggregation. So this is possible only if your aggregation has an inverse reduce function, basically. For a word count, it is pretty straightforward. So for the reduce by key and window, you can specify the aggregation logic, which is the sum, followed by the inverse reduce, which is just removing the counts. So any aggregation function that has like a equivalent a reduce operation, an inverse reduce operation, you can use incremental aggregations there. And apart from the incremental aggregations, the other common thing that developers must do is to use checkpointing of the data itself. Like, you can do a word stream.checkpoint and give a checkpoint interval. So how this will help us, basically Spark will not go all the way till the last 30th minute. Instead, if the checkpoint interval is 10 minutes, so it will go only till the last 10 minutes, and it will read from the checkpoint and then continue its operations. So in that way, it's kind of the performance would be much better. But the biggest drawback to that is you're checkpointing the entire data stream, which can also be expensive. So if you give a checkpoint interval of like 5 seconds, that means like pretty much you're kind of storing all the data in an intermediate storage for checkpointing, which can become a bottleneck. So this is required only if you want to deal with large window sizes, and you can give an optimum checkpoint interval, which is at least I would say 5x the window size. So the next common scenario is basically doing a word count, doing a global word count, or maintaining some state across time from the beginning of time, basically. Like, for example, if the users are browsing through a website and you are collecting all the information and you want to build a user session, like you want to do sessionization basically and kind of maintain a global state of all the sessions that are there. So the two biggest APIs that are available to do state management is basically update state by key and a map with state. So map with state was introduced in Spark 1.6, and that is kind of the preferred approach for doing state management. Update state by key is still available, but its performance is basically proportional to the size of the state. For example, like if you have a state of 1 million words, and if you have a batch that is coming in, which is like 100 words, the performance of update state by key like is proportional to the size of the state, which is like the 1 million words. Whereas map with state, the performance is proportional to the size of the batch, which is like the 100 words. So there is an order of magnitude performance difference between like map with state and update state by key. And map with state is the major thing, is the main thing that people should be using for doing state management. So I'll just cover the slight details about map with state. So this is the example that I talked about where a stream of user actions are coming in. You want to update the user sessions with state and then get a D stream out of it and then keep processing it in a downstream. So the processing can be just storing the state somewhere, persisting the state in Cassandra or some other data sink. Or it can be further downstream for like again pumping it to Kafka to some other downstream process. So the key features of map with state is you can provide an initial state. So if you already have an initial, even before the Spark streaming job starts, if you have a initial state stored somewhere like in HDFS or Cassandra, you can load them as an RDD and provide that as an initial state to map with state. And then you can also specify the number of partitions. If you have a good estimate of like the size of the key space, like if you're going to have 100,000 words or 1 million keys, then you can specify the number of partitions to ensure that the state is kind of evenly distributed across the cluster. And you can also specify a partitioner. The default one is hash partitioner. In case if that doesn't meet your requirement, if you think there will be data skewness because of the way the key space is kind of distributed, you can have your own custom partitioner to make sure that the key space is evenly distributed across the cluster. And finally, you can provide a timeout. This timeout is useful like if you have keys that are not going to be updated in the last say n minutes or n hours. So like for example, if you're building a sessionization application, you don't want to have sessions hanging around for more than like 30 minutes or 1 hour. So you want to kind of remove all the old sessions that are not that doesn't have any recent activity. So having a timeout will help to keep the state in a more pruned way rather than just keeping it grow indefinitely over time. So how that will look, so you have a D stream, and then you can say .map with state is an operator on D stream, and then you can specify, you can provide a specification there. So the state specification takes in the initial state, the num partitions, partitioner, and timeout. These are the 4 things that I talked about. All of them are optional fields. The must field is basically the function to update the state. So what is the logic to basically maintain the state? And that is given by this function, which is defined as follows. So for every event that is coming in, the streaming job will call this function with these parameters: the batch time for that particular event, the key for the event. In this case, in the case of a word count, it's just a word, and the value would be 1 in this case, and the previous state, so the word count so far for that particular key, for this particular key. And then the return value is basically the new key and the new word count for it. So, and one thing to note is this input key and the output key need not be the same, so which means you have more flexibility in kind of managing your key space. So let's move on to the operationalization part. So there are the first thing is checkpointing. There are 2 types of checkpointing. One is checkpointing the data, the other is checkpointing the metadata. So parts of it, checkpointing the data, like talked about during the reduce by key and window. This is required when you're doing computation across a large window size. So for example, here there is a operation that it relies on the previous states here, but you can see here we have checkpointed this particular word stream, so it doesn't go back to all the previous stages. Instead, it reads from the checkpoint, and this gray means these stages are skipped by Spark. So there is no actual computation that happened. So Spark just directly read from the checkpoint and proceeded. So this is one case where it'll be very helpful to kind of have save some have some performance optimization if there is a large window operation that needs to be done on a D stream. The other part is checkpointing metadata. So what kind of metadata? So Spark maintains all the current batches that are being run and all the batches that are queued up to be run. So this is checkpointing the metadata is required if you want fault tolerance and if you want a recovery from from failures automatically. Like for example, if the driver process crashes, then if there is no checkpoint of metadata, then Spark cannot recover from where it left off. So you have to kind of manually, or there will be some data loss that will happen. So the best way to enable the checkpoint is basically say streaming context.checkpoint and then provide a directory to it. So automatically all the active batches that are being processed gets checkpointed to the directory. And whenever the streaming job crashes, you can, again, while creating the context, you can say get active or create, and then provide the checkpoint directory.
What are the options for the directory? Is it still just HDFS, or can it be other things now?
So you can use HDFS and also S3.
S3.
Yeah. So that's about checkpointing the metadata. So the next is achieving good throughput. So a lot of times we've seen like, oh, I have like a 20 node cluster, but the Spark streaming job is still slow or doesn't kind of scale up horizontally well with the my cluster. One of the most common things is this simple streaming job, which has like a receiver, then followed by a map, filter, and then save. The problem here is there is one receiver that is running on one of the executors, which is receiving all the data, and the data resides in that executor. And there is a map and filter operation. Now Spark is going to use data locality to kind of schedule the tasks. Since the data is just in one executor, so it's going to schedule everything in there as much as possible. So there is, even if you scale up the cluster, the streaming job is not going to scale horizontally with the cluster. One common simple solution is immediately after the socket stream, you can do a repartition and then kind of distribute the data across the cluster and then follow other operations on it like map or filter or reduce stuff. The one thing that with that is repartition causes a shuffle, so there is still some performance overhead. A more neater way of handling this would be to basically increase the number of receivers and then union them. So for example, instead of having one receiver, you can have 5 receivers, and so that the 5 receivers run on 5 executors in parallelly receiving the data, and then the further operations on them kind of there is more distribution across the cluster. So this is an example for that, like where you create 5 input streams from the socket, and then you can do a context.union of all those streams. A union is a very cheap operation. It's just an update of the metadata for RDDs to just say, oh, the partitions are located in these executors. So you get a full stream of from all the receivers, and then you can further continue with the further operations on the D stream. So in the case of direct receivers, so with Kafka and other similar data sources, Spark streaming doesn't use the concept of a receiver, simply because Kafka itself is a good buffering system. So why kind of receive the data and buffer that in Spark streaming? So Spark relies on Kafka to do the buffering, and it just notes down the partitions and the offsets that it gets from Kafka to kind of receive the data. So in that case, the best way to kind of increase the parallelism is increase the Kafka partitions. So each Kafka partition gets mapped to a Spark partition. So having more Kafka partitions means more Spark partitions, which is more parallelism in Spark. So far we saw like the parallelism while receiving the data and doing the initial computation, but after shuffle, if you still want to ensure that your cluster is kind of being utilized maximum, for most of the shuffle operations, there is a parameter to specify the number of partitions. So it's always good to kind of specify that to make sure that the data is kind of being evenly distributed. Otherwise, there might be some default number of partitions that might be set like 200, and that'll be the one that is used for all the shuffle. So you might want to have more control over how you kind of shuffle the data around. So as far as debugging a streaming application, in the Spark UI, there is a streaming tab, which is a transient one. This tab is available only if there is a streaming job that is running on the cluster. So it has a wealth of information about all the state of the streaming job that is running, for how long the streaming job has been running, how many records have been processed, how many batches have been completed, and also the number of events that are received per second. And also, if you can, you can also expand this to kind of look at the rate of events for each receiver. So if you have like 10 receivers, you can kind of look at the rate of events for each of them to see if there are any issues. As far as the processing is concerned, since Spark Streaming kind of maintains a queue for each DAG and the batch interval, you might want to ensure that the processing time for each batch is always less than or at least 80% of the batch interval that is provided. So for example, here the batch interval is 2 seconds. The average processing time is 450, so which is 450 milliseconds, so which is good. If it is like 2 seconds or 2.5 seconds, then definitely the Spark Streaming job is going to crash at some point, because it's going to keep accumulating more and more batches that are going to get queued, and at some point it's going to die. And you can see all the active batches here. So here there is only one, but normally if there is batches getting queued up, you can see a lot of batches present here. So that's an indication that like, okay, there is something wrong with the streaming job. And you also have a list of all the completed batches, like the time with the timestamps and the number of events that particular batch processed, along with the processing time for each of those batches. So if you think one of the batches kind of went bad or like went crazy, you can, for example, so this one like took 2 seconds, this one took 3 seconds. So this is an example where like at periodic intervals, I'm doing a checkpoint. So that's why these batches are kind of have higher latencies, because checkpoint has an overhead. But they're going to catch up with other batches, going to be much faster. So overall, the amortized processing time will be still better, but there will be occasional spikes in your in the batch processing time if you are using checkpoint. So you can click on any of these batches, like you can go to the batch details page, which has the details about all your input information, like you have all the offs here. In this case, the streaming job read from 2 partitions from Kafka, and these are the offsets for them. And if you want to drill down further, you can click on any of the jobs that are there. So these are the jobs that are run for this batch. So, and you can finally drill down to the number of stages that were there. So these are the 2 stages that was run for this batch. And this stage had like 1 task, and this had like 2 tasks. So it's a very lightweight streaming job. And if you're interested, you can further drill down from the stages to the tasks. So you can click on any of those stages to drill down into the tasks. So the tasks will have the kind of the lowest granularity possible information where these tasks are run on which executors. So this is a good place to look to make sure that the tasks are evenly distributed in the executor. So this is a very so normally this is a most helpful page, like in terms of trying to find out if the cluster is being utilized properly. So in terms of key benefits of Spark Streaming, because of the way like Spark Streaming schedules the job. So you have like the traditional systems where a distributed cluster is there, and then if there is an unevenly partitioned data that comes in, one node can become a bottleneck. So with Spark streaming, that's much efficient, because for every batch interval, like Spark streaming schedules the task. So if there is one node that is kind of has an uneven partition, so the subsequent batches can still kind of use the available resources to keep moving fast. And of course, you also, for the same reason, with the way the architecture works, you get fast failure and straggler recovery also for free, because if any node goes down, the next batch can always kind of use the other remaining nodes and kind of discard that node, so that the recovery is much faster when compared to other systems, traditional systems. So the other key benefit for using Spark is basically streaming on Spark is you can combine it easily with batch. So if I have a data set, a table or a file sitting in HDFS or Cassandra, I can always load them as an RDD, and then I can join with my stream. So here I'm loading this file into an RDD, and then I have a Kafka stream that is coming in, and I can say Kafka stream.transform. So what transform provides is the underneath RDD in the D stream. So now I have the RDD, and then I can join it with the static RDD that I got from some external source, and then I can do other operations. This is very useful if you have a stream of events coming in, and if you want to just tag the events with some data from external source. So I just want to join it with some external source and then tag it with further information so that I can process it to the downstream consumers. The other most common thing is doing predictions on real-time streaming. So you can do learn a model offline. You can use any of the standard ML algorithms that are available, like any classification or regression or a simple k-means in this example, and then you can apply the model on your stream and do a prediction on a more real-time stream. And the final thing is combining streams with SQL. So you can also kind of, a lot of times I've seen like people use their batch data set, they use data frames or use SQL to do the analysis, and now they want to move it to the kind of on their streams. So the easiest way to do is you have a stream, you can say for each RDD or a transform, which gives the underlying RDD, and then you can create a data frame out of that RDD and copy the exact batch code that you did into this function and continue with the operation. So it's very easy to kind of test your batch code in a streaming fashion. And this is one of the actual main motivations for the next version of streaming in Spark, which is the structured streaming, which is coming in Spark 2.0. It's basically to say like I want to just do a simple streaming job. I don't want to reason about all this other things that are happening like D streams and stuff. All I'm doing is reading from this file and reading from this source and writing it to this sink, doing some SQL operation or some ETL operation in between. Instead of saying SQL context.load, I should just say SQL context.stream, and everything will work as it is. So that's one of the biggest motivations for structured streaming, which is coming in Spark 2.0. Yeah.
Structured streaming at 2.0 is in addition to the existing streaming capabilities, is that correct?
Yes, so this is going to remain as it is. Structured streaming is a whole new approach for streaming, and we'll kind of continue to invest time on that to make sure to keep improving that based on the lessons that is learned from these streams.
Well, it's important as we migrate our apps.
Yes. So that's all I had. Questions? Yeah.
Yeah. Is there a way to drop tasks if sometimes you have batch jobs that are just heavy and there's There's no way around it. Is there a way to actually control the way the task is scheduled?
So you want to drop the tasks or kill the task, or
Yeah, kill the task.
there are ways you can do. You can combine. So there is a streaming listener interface that you can implement yourselves that gets all the information about whether a batch is completed. And if you don't get information from that listener interface for a specific batch, you can then force a particular batch to kind of throw an exception so that it proceeds to the next one. So it's a very hacky way. There is no straight API that is available, but yeah, you can do it if you are keen. Yeah.
One question. A common use case that you need to join big data sets SRTT with some small dictionary to use broadcast language. But what you can use Spark streaming
Okay.
to broadcast, say, small change data. So, like the same scenario as RDT joined with broadcast variable, but in case of Spark streaming, I may need to change the broadcast variable time to time.
Yeah, so one way, there are different ways to do it, but one way would be, so basically, one way would be to say like, you can do a broadcast hash join. So you don't need to explicitly broadcast your small table. You can do a simple join of a large table with a small table, and then you can specify a broadcast hash join parameter. So automatically Spark will figure out, oh, the right table is small, so let me do a broadcast hash join.
So maybe I can say more concrete. I have a stream of events,
Okay.
thousands per second.
Okay.
And I have several hundred definitions to filter whether events in real time. So even what I try to avoid shuffle before join.
Okay.
So I do process per partition first, and reduce number of events.
Okay.
Monitor only process after that. So what I need to distribute data across all nodes. In a static Spark job, I do that using broadcast variable.
Okay.
What I can do is Spark streaming to update as such variable.
The best in that case would be to use the transform function. So whatever you write outside of any of the operations doesn't get picked up by Spark streaming, right? Because the scheduler kind of picks up only the DAG of operations. And that's why the transform function was introduced. So inside the transform, you can have a non-volatile kind of RDD, which refers to your small table, and then you can broadcast that, or a non-volatile any variable to your data set, and you can broadcast that inside the Spark, inside the transform to make sure that, and you can also make it more sophisticated because the transform also gets batch time. So you can do it once every 30 minutes if your data is changing only occasionally.
Only thing, if I rebroadcast, I will field data manager with all choices how to clean up. What's the correct time to clean up all variables?
That depends on how frequently your data, the small data gets updated. I'm not sure on top of my mind like the best way to clean that clean the data. I need to look into that.
Also, related question: can I use accumulator
You can use accumulators, but accumulators are not fault tolerant. So if a task fails and gets rescheduled, it'll recount. So if you want exact correct counting, accumulators is not the best thing to do. Instead, rather use the dstream or RDD to do the actual counting.
That's time. Thanks again.
All right. Thank you.